So good day to all of you. So we're already finished with chapter 2, which is all about operating system structures. So now we're in chapter 3, which is solely dedicated about the processes. So what is processes doing inside the operating system? So let's delve and let's learn more about these processes. So chapter 3 processes and its contents are process concept, process scheduling, operations on processes, interprocess communication or IPC, IPC in shared memory systems, IPC in message passing systems, examples of IPC systems, and communication in client-server systems. So the objectives for this chapter are identify the separate components of a process and illustrate how they are represented and scheduled in an operating system. Describe how processes are created and terminated in an operating system, including developing programs using the appropriate system calls that perform these operations. Describe and contrast interprocess communication or IPC using shared memory and message passing. And then design programs that uses pipes and POSIX shared memory to perform interprocess communication. Describe client-server communication using sockets and remote procedure calls or RPC, and design kernel modules that interact with the Linux operating system. So first is we have the process concept. An operating system executes a variety of programs that run as a process. So as the definition for the process, it is a program in execution. Process execution must progress in sequential fashion. So it should not be in random fashion. So process has multiple parts such as the program code, also called the text section, current activity including program counter, processor registers, and then we have the stack containing temporary data such as function parameters, return addresses, and local variables. For data section, we have this contains the global variables, and then we have the heap containing memory dynamically allocated during runtime. So program is passive entity stored on disk, or this is the executable file while the process is active. So what's the difference between a program and a process? So a program becomes a process when executable file is loaded into memory. So if you have a program that is installed in your operating system but you're not using it, currently using it, it means that it's just a program. It's just in the hard drive. While, for example, if you're going to run that program and it will be loaded in memory, so that means that's not a program anymore, but an execution. So example of this is, but an execution, so that is called a process, a program in execution. So for example, so this PowerPoint presentation or the slideshow presentation that we have, if I'm not using it, so it is a program. But since I'm using it currently, as you can see, so meaning that slideshow presentation that I am using is now a process because this presentation is loaded in memory. And then execution of program started via GUI mouse clicks. So of course, the icon of the program, if you're going to click it, then it will be executed, or the program will be executed, and this will be loaded into memory. So another one to execute the program is by using the command line entry of its name, as you can remember with chapter 2, in which I've demonstrated to you of how to run a program inside a command line interpreter, such as typing its name, whatever the spelling it is, it should be correctly spelled, and then just press enter, or the name, and then we have .exe. So of course that's an executable file. And then one program can be several processes. Consider multiple users executing the same program. Example is you have two slideshow presentations and you want to open it at the same time. So that instance, that two instances of the slideshow presentation, that is already one program, can be several processes because the slideshow presentation for presentation A is different from presentation B, but they're still using the same slideshow presentation loaded into memory. That's why it is a process. Okay, so this is the process in memory. So as enumerated a while ago, the parts of memory, we have the stack, heap, data, and text. And there is an arrow with heap and stack, meaning stack and heap can allocate more space if it is needed, as long as there is still free space in memory. So we have an example to illustrate the memory layout of a PC program. So the libraries for standard input output and standard library are not allocated in the memory of of the process. And then we have int x and int y. Int x, since this has no value, so it will be stored in uninitialized data, while int y, an integer, is equals to 15. It already has a value before the start of the execution of the program. It will be stored in initialized data. And then our main, then it has an integer argc and character argv, a pointer, and at the same time an array. So this will be put in the highest um, location in the memory. And then we have int asterisk values for pointer, and int I, this will be put in stack. And then values is equal to integer, then memory allocation, so that's why it's called malloc. Then size of int times 5. So this will be put into heap. And then for and return will just execute. So meaning the variables that are declared in the program will have their corresponding there will be stored in the corresponding parts of the process. Okay, next is we have process has many states. So as a process executes, it changes state. So we have new, the process is being created. And then we have running, the instructions are being executed. We have waiting, the process is waiting for some event to occur. We have ready, the process is waiting to be assigned to a processor. And terminated, the process has finished execution. So these are the 5 states of a process. So we have a diagram. So for the next slide, so if it's new, this will be loaded into memory. And then if it's already admitted to the memory, then it will be ready. And then the scheduler dispatch, because of the scheduler dispatch, it will be running. Here, the program is already in execution, so it's called already a process. And then if there is an interrupt, for example, if another program needs the attention of the CPU, so from running, it will be ready. And then, or if it is running, then there is an IO or event wait, so waiting. And then after the IO or event completion, it will return to ready. And then again, it will run if you execute the program. And then, for example, if you're going to close the program, so you're going to exit and then terminate. So for terminated, all the allocated resources that is used by the process must be returned so that other process can use that resource. So to further illustrate at least, so you can understand how does the process changes from one state to another. So let's have a demonstration. Okay, example, assuming that we have no presentation here and no recorder here. So what if, for example, I want to run the word processor program? So of course, this is not yet a process because I haven't clicked it yet. So as we can remember, we have the new and then ready. So let's click the icon. So once I clicked, so that will be new and then it will be ready. So actually, because the processor nowadays of the computers are fast, you can no longer see the difference between um, new and ready. Okay. So let's click. So you'll see the splash screen of Microsoft Word starting. So that's new. And then it will be ready. Okay. So it's only loading its add-ons such as Grammarly and processing. So meaning it is assigned to the processor. So new new and ready is already happening while this splash screen is here showing you. So actually, of course, um, you don't know what is happening in the background. So that's I'm explaining the new and the ready. So actually, you are already in the state of the running state. So let's return. So as I've said, new when you click, once you click the icon, that's already new, and then it's already admitted to the loaded in memory, and it is already processed by the processor, so it's already in the ready. So since Microsoft Word is already running, so it's already running. Okay, so let's return, and then going to open a blank Word document file. So please wait, be patient because my laptop is a little bit slow. Okay, so this. Okay, actually this is already running. Of course, it will still run if you're going to type words on it. Okay? So this is already on the running state. So next is, for example, what if running then ready? So from running to ready, we cannot really I cannot really explicitly show it because of course interrupt, this is internal. So actually what I'm doing here, so here for example I'm typing, so that's running, and then I'm going to switch here to Microsoft or to the slideshow presentation. So that is already from running to ready because I've switched from one program to another. Actually, your keystrokes in the keyboard, that is already an interrupt. So from running to ready, so here in my example, my slideshow presentation, it is running while my Microsoft Word, it is in ready state because that's not the active process. The active process here is the slideshow presentation. So that's the from running to ready. And then vice versa again, if I return to the Word document, so this is the running process while the slideshow presentation is ready. So I hope that you are understanding, but for old computers, like it's like that, but because most of the computers now, they have this course, so it can execute at the same time. But I hope that you get the idea of the ready and running. Okay, for this is evident for processor that that has only one core. Okay, so let's return. So how are we going to illustrate running to waiting? So for example, so we have this, and then you want to save. So let's save as. Example, let's go to downloads, for example. Okay, so let's return. So this is running from waiting. Why is it running for waiting? Because you cannot type because there is a child. Actually, this save as is a child process of Microsoft Word because you're going to save a file. And then what if you want to exit or close? Can you close the application? No, because you have a child process in execution. So this example is from running to waiting because the process, the Microsoft Word is waiting for you to execute the save as command. And then okay, I've opened another we have another child of the child process save as. Okay, if you're going to click the close for save as, you cannot um, close because you have another, because the child process has another nested child process inside. So again, it is waiting. Okay, so for you to execute again the main process, you have to, it's either save this file or you exit. For example, I don't have any plans to or rather example, let's save this for the sake of learning. So if we're going to save it, So of course, relatively it's already fast. So from running to waiting, waiting for example, waiting for you to save, and then after saving IO or event completion, it will return to ready. As you can see, it's already again in the Word document and you're ready to type. Okay? So again, ready, then automatically it will be again in running because the program, or the rather the process is already running. And then if you're going to close the program, so for we have this close, so it will invoke the command exit, and then the process is already terminated. So again, the Word document is returned as a program. Okay. So that is an example of a process state. So I hope that you understand how does the process goes to new, ready, running, then waiting, and then terminate. So this process state is the same for all programs or processes rather. Again, process is a program in execution. Okay, next is we have the process control block, or the PCB, information associated with each process, also called task control block. And then the process states, as already demonstrated previously, is we have the running, waiting, and others. Then program counter, location of instruction to next execute, and then CPU registers, contents of all process-centric registers, and then CPU scheduling information, priorities, scheduling queue pointers, and then we have memory management information, is memory allocated to the process. And then we also have the accounting information, the CPU used, clock time elapsed since start, time limits, and then we have the input-output status information, IO devices allocated to process, list of open files. So this is an example of a diagram of a PCB. So these are the parts. So this is an example for process state, process number, program counter, register, memory limits, list of open files, and others which are not included. So these are the common parts of the process control block. So next is we have threads. So far, process as a single thread of execution. Consider having multiple program counters per process. So multiple locations can execute at once and multiple threads of control. So we have threads. So must then have storage for thread details, multiple program counters in PCB. So explore in detail in chapter 4. So actually there is a separate, if there's a process, there are threads. Imagine threads is like this. We have a program and then it becomes a process because a program in execution. This process is still divided into smaller parts that can be executed in parallel. So these small parts of the process, these are called the threads. So we're going to delve on that topic on the next chapter. So next is we have, how about the process representation in Linux? So represented by C structure task underscore struct. So as you can notice, the operating system program language is more built on C. So we have PIDT underscore PID. This is the process identifier, long state, that's state of the process. Unsigned integer time underscore slice, the scheduling information. Struct task underscore struct pointer, a parent, the process is parent. Then struct list underscore head children, this process children. Struct files underscore struct files, another pointer for list of open files. And struct underscore struct, another pointer address space, or the memory allocation. So this is the illustration for this is for example of the current executing process, and they have, for every process, they have this process information. So this is the, unlike with the process control block, this is the structure for process in Linux. So next is we have process scheduling. So maximize CPU use, quickly switching processes onto CPU core. Then process scheduler selects among available processes for next execution on CPU core. Meaning for CPU must not be idle. From time to time, it should have a process that is to be executed by the CPU. And then maintains scheduling queues of processes. So we have ready queue. So the ready queue, these are set of all processes residing in main memory, ready and waiting to execute. And then we have wait queues, set of processes waiting for an event such as input or output. And then processes migrate among the various queues. Okay, we have an example here. So this is the ready queue. As it said, it is already loaded in the memory, ready and waiting. So we have the pointer for PCB7. This is the process control block number 7, and this is 2. And then they are ready to be executed, while there are programs that are in the wait queue, meaning they still need another resources such as IO. So that's why they are in the waiting queue. But once they've have the resources that is needed, then they will be connected here for the to the ready queue. Okay, next is we have representation of process scheduling. So actually, we have another topic. How does the CPU schedules the processes to be executed? So what are its priorities? How does the CPU know that? So this is the process to be executed first and then the next and so on and so forth. Is it really in sequential fashion, or is there a condition for the last process to be executed first? So we're going to study that in another chapter. So, for the meantime, this is the illustration of the process scheduling. For example, you have a process and it already has the allocated resources. So, it's already in the ready queue, ready to be executed by the CPU. And if it's already finished, so it will exit the CPU. So, what if the process needs additional input-output? So, it will exit the CPU and then will request for IO, and then it will line up for the IO wait queue. And then after it has already acquired the needed input-output, then it will return to the ready queue. And if there's no problem and it is already completed the execution, it will exit again. What if another process, for example, the CPU only allocated for this example 5 seconds of execution, but the process needs 10 seconds of execution. Of course, since it only gives 5 of its time to all of the processes, for example, so it will exit the CPU and then time slice is expired, meaning, or rather, it still needs another 5 seconds to finish its execution. So it will line up again to the ready queue. And if it's already okay and it's already finished the execution, again, it will exit the CPU. So another, what if the process created a child process? So again, it will exit the CPU, and then it will we have the child termination wait queue, and if the child has already terminated, again it will return to the ready queue, the main process. And of course, if there's nothing wrong, it will execute, and then it will exit the CPU. And last one is, for example, a process has an interrupt, so wait for an interrupt, then it will line up in the interrupt wait queue, and then after the interrupt occurs, and then it will return again to the ready queue until it will be finished and it will exit the CPU. So that is the process scheduling. So next is we have the CPU switch from process to process. So a context switch occurs when the CPU switches from one process to another. So, for example, we have an operating system and there are example, strictly for this example, 2 processes that is loaded in memory. So, for example, process P sub 0 is executing, and then there is an interrupt or system call. So, it will save on the process PCB and PCB sub 0. Okay? And there is another process which is P sub 1, which will be reloaded the state, and then process P sub 1 will run while P sub 0 is idle for while there is execution. And then what if again there is an interrupt or system call? So it will save state into PCB sub 1, okay? And then reload the state of P sub 0, and then it will execute. Okay. So this is the process of context switch. So for you to understand context switch, I have this um, laptop when I was in college. So it's already a very old laptop at that time. The existing processors at that time is already Pentium 4, so that's already very fast at that time. While I have this laptop which is Pentium 1, so aside from my very old model laptop, at home I have a Pentium 3. So I know the performance level of Pentium 3 in compared to Pentium 1. So with Pentium 3, I can already have this multitasking. Example, while actually you're doing that, I think. For example, while you're typing, for example, in a Word document, and then you have a music playing. So actually, what does those computers at the time doing is this context switching. So while you're typing, it's playing, it's doing this context switching. The question now is, why is that us people never realize it that the operating system is actually doing the context switching between, for example, between your word processor and your music player, because because it's already doing it fast. The context switching, it's too fast. As I've said, computers are operating not in seconds, but in nanoseconds. So that's why you will never notice that there is a context switching happening between those two processes that are running in memory. So, in relation with my old laptop, so of course, I want to do that while doing something. I want to listen to music. The funny thing there in my laptop is that when I opened my music player and the word processor, so I opened first the music. So there's music playing. Then I opened the word processor. So it's already loaded in memory. The music is still playing. The funny thing here is when I switch to the word processor, the music stops. And then when I switch to the music player, of course the music played, but I cannot type. So it just really means that Pentium 1 is not is it actually does have only one core for the processor. And because of course you can really see that the operating system is switching from one process to another. So that's already a classic example of context switching. So that's very obvious because Pentium 1, of course, it's a very slow processor. But while Pentium 3, while of course, why if I'm switching from, for example, the music player is in the background while you're typing, still you're still hearing the music because the processor can context switch fast because of course the Pentium 3 is faster than Pentium 1. So the question is today is that the is still the processor using this context switch, of course, but again we can never notice that anymore because the CPU operates at nanoseconds at very fast speeds. So that's why it for us it looks like it's running the processes concurrently. So it's not just limited to two processes. Imagine you can open all the processes, but of course you can if for example you open 10 processes, you can already notice that there is the response of the CPU is a little bit it's a little bit slower. It's just like, for example, for people, what if you're cooking and then you're ironing your clothes, you're watching TV, and then your child is crying and then all at the same time. Of course, for a person, it's very difficult. But for you're going to context switch at that time, but it's very difficult. Actually, this is a theory I've read that multitasking is bad for our brain. It loses our focus. So actually, multitasking is not advised for people. But this is just an example. But of course, mm, CPU can do that. So it's just fine. But of course, if you're going to open 10 processes or more, depending upon your CPU, it still can execute and have the context switching, but you'll notice that it will become a little bit slower. So that is the context switching. Okay, so when CPU switches to another process, the system must save the state of the old process and load the saved state for the new process via a context switch, as already illustrated and as I've shared with my example. So if you return, for example, if you return to another program, you can continue with what you've started there. So that's the meaning of saving the state of the old process and load the saved state for the new process via the context switch. As you can remember, when I open my word processor. So when I switch, I already type, then I can type. It's not that if I switch, then I'll start again to type. No, you can start again where you ended typing, and also for the slideshow presentation. So if I switch again to the slideshow presentation, I will continue where would I stop. So this is the what does that this is what does that mean with the illustration of saving the state of the process and load the save state for the new process via a context switch. Then context of a process is represented in the PCB. Then context switch time is overhead. The system does no useful work while switching. So as you can see, if there are switching, for this one, switching, and you can see it's idle. But for processors nowadays, it's very minimal because they work in nanoseconds. For us, it does not matter because it does not affect the performance or the response of your computer. So the more complex the OS and the PCB, the longer the context switch. And then time dependent on hardware support, some hardware provides multiple sets of registers per CPU, so multiple contexts loaded at once. Specifically, if of course, if your CPU is already as powerful and has many transistors or it has many cores, so it will not have a problem with context switching. Okay, next is we have multitasking and mobile systems. So some mobile systems, such as early versions of iOS, allow only one process to run, the others are suspended in the background. Due to screen real estate, user interface limits iOS provides for a single foreground process controlled via user interface. Then we have multiple background processes in memory running but not on display and with limits. And then limits include single short task, receiving notification of events, a specific long-running task like audio playback. And then Android runs foreground and background with fewer limits such as background process use a service to perform tasks. Service can keep running even if background process is suspended. And service has no user interface, small memory use. Even in our computer, in our personal computer, so this is an example of a foreground process, this slideshow presentation, because it's running. But the other background processes, as you've already seen with Task Manager, such as the service host, the ones in the networking, all the system programs, these are all running in background to make your operating system functions well. Okay, operations on processes. So, system must provide mechanisms for process creation and process termination. So, for process creation, parent process creates children processes, which in turn create other processes, forming a tree of processes. So, I already illustrated it when I'm going to try to save the Word document, and then I opened another selection in the Save As, the general options, and then another window was opened, or another dialog box rather window was opened. So that's already a tree of processes. So generally, process identified and managed via a process identifier. So we have resource sharing options. Parent and children share all resources, of course. Children share subset of parents' resources, or the parent and child share no resources. And then the execution options, parent and children execute concurrently. So actually, it does not happen with the example that I try to close the save as window, but it doesn't even though you already the mouse cursor is already there, but you can't close because there is another child process that is open that you need to execute or you need to terminate. And then this is what is happened with the illustration with my demonstration is parent waits until children terminates. As you can see, even the word document, the word processor, I'm trying to close it, but it does not work because the save as child process is still open. So we have a tree of processes in Linux. So this is the parent process, and then this is the children process. And then login D and SSHD have their own set of other child processes. So Windows can also have a tree of processes. So continuation for process creation is also we have the address space, child duplicate of parent, and child has a program loaded into it. So for Unix examples, so fork system call, as you can recall, this creates new process in Unix. Then exec function, which is a system call used after a fork, after creating a process to replace the process memory space with a new program. And then parent process calls wait for child to terminate. So this is the process. So the state. So the parent we have fork. So for fork rather F, it creates a new process, a child process. So child PID is equal to 0. And then the child executes. So while the child executes, the parent is going to wait. It's just like with the illustration with the word processor. So it will the parent will wait after the execution of the child process, and then after the execution of the child process it will exit, and then it will return to the wait, and then in which the parent has already rather the child has already finished its execution, then the parent resumes its own process, or any commands that it will execute. So we have the C program forking separate process. So this is for the Unix. This is the code for creating a new process. And then this is the code for creating a separate process via a Windows API. So this is its source code. And then next, if we have process creation, we also have process termination. So process executes last statement and then asks the operating system to delete it using the exit system call. Return status data from child to parent via wait. Process resources are deallocated by operating system. So that the function of process termination is for the process to return the resources that it has used to the operating system. So parent may terminate the execution of child processes using the abort system call. So abort. So parent and child then abort. The funny terms, okay? Some reasons for doing so. So the normal termination is exit, meaning that the process will return its allocated resources to to the operating system. But there is a time that the abort system call is invoked. So the reasons are child has exceeded allocated resources, and then task assigned to child is no longer required, and then the parent is exiting and the operating system does not allow a child to continue if its parent terminates. So if there is an error, that's why abort system call is invoked. So these are the cases in which abort system call is invoked or executed. So some operating systems do not allow child to exist if its parent has terminated. So that's why, for example, for our illustration, for the demonstration, so it's impossible, for example, for the parent to terminate if the child is still existing. So before the parent terminates, the child must be executed or terminated. If a process terminates, then all of its children must also be terminated, of course. So we have cascading termination. All children, grandchildren, if ever there is, are terminated. Then the termination is initiated by the operating system. The parent process may wait for termination of a child process by using the wait system call. The call returns status information and the PID of the terminated process. So we have PID is equal to wait and then status. So if no parent waiting or did not invoke wait process, then the process is a zombie. So if parent terminated without invoking wait, then the process is an orphan. So that is the difference between a zombie and an orphan. Okay, next is we have Android process importance hierarchy. So mobile operating systems often have to terminate processes to reclaim system resources such as memory. So I have said all the resources that the process has used must be deallocated so that other processes can use those resources. So from most to least important, we have foreground process, visible process, service process, background process, empty process, and Android will begin terminating processes that are least important. Why is the foreground process the the most important? Because this is seen by the user of the phone, of course. Okay, next is we have multi-process architecture for Chrome browser. So many web browsers run as a single process, so some still do. If one website causes trouble, entire browser can hang or crash. So that's the problem for a web browser that run as a single process. What if you have 5 tabs and one of them has an error? So it means the web browser will restart itself because one of its tabs or the site has an error or it has crashed or hanged. So an example of a multi-process architecture is the Google Chrome browser. It is multi-process with 3 different types of processes. So we have browser, process manages user interface, disk and network I/O. Then we have renderer, process renders web pages, deals with HTML, JavaScript, a new renderer created for each website opened. Runs in sandbox restricting disk and network I/O, minimizing effect of security exploits. So we also have plugin process for each type of plugin. So this is an example for Chrome. So for Chrome, osbook.com, operating system, we have 4 tabs, meaning this tab represents a separate process. So for you to illustrate if this really is happening with Google browser, so let's open a Google Chrome browser. So again, so let's click Google Chrome. Okay. I've saved the state of my previously opened Chrome. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 tabs opened. Okay, actually, my husband is saying that's why your computer is slow because you have 14 tabs open simultaneously in a Chrome browser. Okay, so we have 14 tabs. So let's check our task manager if is it true that the Chrome browser is a multi-process architecture. So let's open our task manager. Then, where's Google Chrome? So let's wait. Okay, this one. For background processes, so that we have Google Chrome. So it's initially loaded as 12. 13. Okay. So I don't know where's the other tab, but it's 14. Okay. Okay, so 14, 15. So, okay, I really don't know the behavior of the operating system. Why is it 13 then it becomes 14? It depends upon the execution of the Google Chrome. But as you can see, if you have many tabs that are opened, so this will be reflected, meaning this individual Google Chrome are the tabs. And then sometimes since it's newly opened, sometimes if your Google Chrome is already open for a long time, it will also exceed its number, not just 12, because of the renderer of the plugin. So we have this example, and as you can see, of course, because it has many tabs, and this Google Chrome tabs are also separate processes. You can see that the CPU is working its own mind of 50, 47, then the memory is 44. So that is why, though the advantage of this multi-process architecture by Google Chrome is that, for example, if a tab has crashed, it will not affect other tabs. And relatively, if you're using Google Chrome, it is faster because it's separate. The tabs are separate processes. But it's not really a problem. But the only downside of a multi-process architecture of Chrome browser is that it affects, of course, because it has many processes. Per tab is a process. It will allocate more memory, more resources such as memory, CPU. So that's why you can see in the task manager that the CPU has become busier because these 13 processes are running. So, okay. So that's why actually when I'm doing my presentations here, I always turned off the Chrome browser. But for this example, so that is to show that Chrome browser is a multi-process architecture. So let's close, and again, let's close my tabs. Okay, this is the my everyday tabs. Of course, the Google Classroom, and then other email and other hobbies. Okay. Okay, let's return in our presentation. Okay. So next is we have interprocess communication, so or the IPC. Processes within a system may be independent or cooperating. Cooperating process can affect or be affected by other processes including sharing data. So reasons for cooperating processes is we have information sharing, computation speed up, modularity, and convenience. So cooperating process need interprocess communication or IPC. So two models of IPC is we have shared memory and message passing. So the communication models for shared memory, process A and B, they have this shared, of course, that's why it's called shared memory. Process A is accessing this memory and also process B is accessing the shared memory. While the message passing is, we have two processes here, for example, and then we have a message queue and they're accessing the message queue, process B and process A. So that is message passing. Okay, so for cooperating processes, independent process cannot affect or be affected by the execution of another process. So that's why they are called independent process. While cooperating process can affect or be affected by the execution of another process. So advantages of it, actually it's already repeated. So reasons or advantages of process cooperation is information sharing, computation speed up, modularity, and convenience. So we have this producer-consumer problem. So paradigm for cooperating processes, producer process produces information that is consumed by a consumer process. So we have this term unbounded buffer places no practical limit on the size of the buffer. So so it has no maximum level. So also we have bounded buffer assumes that there is a fixed buffer size. So for interprocess communication shared memory, an area of memory shared among the processes that wish to communicate. As you can see with the illustration with shared memory, So process A and B accesses the same memory. So the communication is under the control of the user's processes, not the operating system. Major issues is to provide the mechanism that will allow the user processes to synchronize their actions when they access shared memory. So synchronization is discussed in great details in following chapter 6 and 7. So we have this bounded buffer shared memory solution. So meaning bounded buffer, it has a maximum number of size. So define buffer size, which is 10. Then type def is struct. So whatever the contents of this data structure, and then item buffer size, int in is equal to 0 and int out is equal to 0. The solution is correct but can only use buffer size minus 1 elements, which is 9. So this is the code for producer process. So item next underscore produce while true. Okay, while in plus 1 modulo buffer underscore size is equal to out, do nothing. Meaning, if the producer will add another item, it will do nothing while, because the buffer size is full. So that's the meaning while why the comment is do nothing, because you cannot add again, it's a bounded buffer, it has a maximum. For example, the maximum number is 10. You cannot add additional item if the buffer size is already full. But if it's not full, buffer in is equal to next underscore produced, then in is equal to in plus 1 modulo buffer size. So if it's not full and the process will produce the item, it will just add to the buffer size. Again, if it's not full. So that's the code for the producer process. Okay, while the consumer process in shared memory, so item next underscore consumed, while true, then while in is equal to out, do nothing. So what does the consumer do? The consumer consumes or use the item. What's the meaning of in is equal to out and then do nothing? It means the buffer size is empty. So since the buffer size is empty, the consumer cannot consume any item because the buffer size is empty. But if it's not empty, next is equal to next underscore consumed is equal to buffer out. Out is equal to out plus 1 modulo buffer underscore size. So this happens if the buffer has items that the process consumer will consume that item. Okay. Okay, next is we have what about the IPC for message passing? So mechanism for processes to communicate and to synchronize their actions. So we have the message system. Processes communicate with each other without resorting to shared variables. So IPC facility provides two operations. We have the send, then the contents or the parameter of the send is the message, and receive, the parameter of the receive function is also a message. The message size is either fixed or variable. So, for message passing, if processes P and Q wish to communicate, they need to establish a communication link between them. So, because of message passing, exchange messages via send or receive. What are the implementation issues? So, how are links established? So, that's the first question. Can a link be associated with more than two processes? Because for this example, we have strictly two processes. What if we have 3, 4, or more? And then how many links can there be between every pair of communicating processes? And then what is the capacity of a link? Is the size of a message that the link can accommodate fixed or variable? And then is a link unidirectional? For example, for unidirectional, only P can send the message while Q will always receive the message. Q cannot send message going to P. So that's unidirectional or bidirectional, of course. P can send and receive, and Q can also send and receive message. Okay, implementation of communication link is physical via shared memory, hardware bus or network, or it can also be logical, direct or indirect, synchronous or asynchronous, automatic or explicit buffering. So first is we have direct communication. So processes must name each other explicitly. Okay, so send, then the parameter is P and message. So the meaning of this function is send a message to process P. Okay. Then receive Q, then message. This means receive a message from process Q. And then properties of communication link. Links are established automatically. A link is associated with exactly one pair of communicating processes. So that is the direct communication. So the limit is exactly one pair of communicating processes. And between each pair, there exists exactly one link. And then the link may be unidirectional, but is usually bidirectional. So bidirectional, P can send and receive, and Q can also send and receive a message. So again, direct communication is strictly for one pair of communicating processes. So what is the other one, the indirect communication? So messages are directed and received from mailboxes. So instead of direct communication from one process to another, there is a mailbox, or also referred to as ports. So each mailbox has a unique ID. Processes can communicate only if they share a mailbox. So properties of communication link. Link established only if processes share a common mailbox. A link may be associated with many processes. So that is the advantage of indirect communication. With direct communication, it also has limits of one pair. So only two processes can have a link, while indirect communication, it can have many processes as long as this process is has the common mailbox. Many processes can share that common mailbox. And then each pair of processes may share several communication links, and links may be unidirectional or bidirectional. So operations, so create a new mailbox or port, send and receive messages through mailbox, or destroy a mailbox. So primitives are defined as, so send a message. So for direct communication, the first parameter is the process, while for indirect communication, send a message to mailbox A. So the first parameter here is the mailbox. And also for the receive A and then message, receive a message from mailbox A. So we have the mailbox instead of processes here, the name of the processes. So mailbox sharing. So as I've said, it can have two or more processes that share a mailbox. So for this example, we have three. P sub 1, P sub 2, P sub 3 share mailbox A. P sub 1 sends. P sub 2 and P sub 3 receive. Who gets the message? Actually, um, it can be 2 and 3. But the solution to save, for example, resources, so allow a link to be associated with at most two processes. So that's the first solution. The other is allow only one process at a time to execute a receive operation, and then allow the system to select arbitrarily the receiver. Sender is notified who the receiver was. So these are the solutions for who gets the message. Okay, next is we have the synchronization. So message passing may either be blocking or non-blocking. So blocking is considered synchronous. So synchronous means it has a timing, it has a time interval before it sends or receives. So that's why it's called synchronous. So we have blocking send. The sender is blocked until the message is received. For example, the sender sends the first message, but it is not yet received by the receiver. The sender is blocked and it cannot send another that same messages, so as not to flood the receiver, because the receiver has not yet um, received the message. And we also have blocking receive. The receiver is blocked until a message is available. So for the receiver, us to not to wait forever if there is a new message that will be sent. It will only receive a message if a message is available. But until then, the receiver is blocked. So that is blocking. What about non-blocking? So it is considered asynchronous. So it does not uh, follow a time interval. It actually, it's asynchronous means anytime. So what's the difference between blocking send and non-block and between non-blocking and blocking send? For non-blocking send, the sender sends the message and continue. So for example, the sender sends the first message and it will send another message, and then there is no blocking compared with blocking send. So it can flood the receiver with how many messages the sender decides to send a message. And then we have a non-blocking receive. So the receiver receives it's either a valid message or a null or an empty message. And then different combinations are possible. If both send and receive are blocking, we have a rendezvous. Okay, it's not rendezvous, okay? That's a French term or a French word meaning. So, a rendezvous in a real world situation, rendezvous means a meeting point, a meeting place. You can say it's a date. You can think of it as that. But the definition here for operating system is rendezvous. Rendezvous, okay? Rendezvous. In interprocess communication, when blocking mode is used, the meeting point at which a send is picked up by a receive. So it's also like in a real world example, a meeting point. Okay, next is we have the producers for shared memory. So message next produced for this is the process or the to be run, the line to be run to and C. While true, produce an item in next underscore produced and send next produced for the message. So next send next underscore produced. And then for the consumer, so since for this example, producer will send the message, then the consumer, so message next underscore consumed while true, receive next consumed, so consume the item in next consumed. So this is for while the consumer, it will receive the message. Okay, next is we have buffering. So queue of messages attached to the link, implemented in one of three ways. We have the zero capacity. No messages are queued on a link. Sender must wait for receiver. So it's a rendezvous. Then we have bounded capacity, finite length of n messages. Sender must wait if link is full. So that's the bounded capacity. While unbounded capacity, we have the infinite length. Sender never waits. So what are the examples of IPC systems? So in POSIX, so POSIX shared memory. So process first creates shared memory segment. So these are the memory segment that the POSIX will use. So we have also used to open an existing segment and set the size of the object. So we have this line of code truncate, then shm underscore fd 4096. So use mmap to memory map a file pointer to the shared memory object, and reading and writing to shared memory is done by using the pointer returned by mmap function. So this is the code for IPC POSIX producer. Okay. And this is the code for the IPC POSIX consumer. Okay, another is what about the IPC systems in Mac? So Mac communication is message-based. Even system calls are messages. Each task gets two ports of at creation, the kernel and notify. Then messages are sent and received using the Mac underscore message function. Ports needed for communication created via the Mac underscore port underscore allocate function. Send and receive are flexible. For example, four options if mailbox is full. It's either wait indefinitely, wait at most n milliseconds, return immediately, and temporarily cache a message. So this is the code for Mac messages. So it is a data struct. And then we have for the port for the client and server. Then this is for the MAC message passing for the client. This is the code for the client. And then this is for the code for the server of MAC message passing. Okay, how about IPC systems of Windows? So message passing centric via Advanced Local Procedure Call or LPC facility only works between processes on the same system, uses ports like mailboxes to establish and maintain communication channels. Communication works as follows. The client opens a handle to the subsystem's connection port object. The client sends a connection request. The server creates two private communication ports and returns the handle to one of them to the client. And then the client and server use the corresponding port handle to send messages or callbacks and to listen for replies. So this is the illustration of the local procedure call in Windows. So client will have a communication request to the connection port and it will be handled by the server, or the client communication port handles the client and the server communication port is handled by the handles the server. And then it can also be shared section objects greater than 256 bytes between client and server. Okay, next is we have pipes. So, acts as a conduit allowing two processes to communicate. The issues for pipes is communication unidirectional or bidirectional? So, one-way or two-way? So, in the case of two-way communication, is it half or full duplex? For half duplex for two-way communication, it means that you cannot send, for example, you cannot send the message at the same time. So, if you cannot send process P and process Q send messages at the same time, if they can only use the pipes alternately or not simultaneously, then it is half duplex. And if it's full duplex, the sending of P and Q can be simultaneous. So it can pass at the same time. It's just like the road. If our road is half duplex, even it's two-way, it's like a one-way road. For example, if it is one-way, for example, if the car on the left has arrived earlier than the car on the right, or rather going to east and going to west. So if the car going to east has arrived earlier than the car going to west. So, the car going to east will use the road first. And after all the cars, or if there is a control that 5 cars only, so that the cars going to the west will also use the road. So, that is half duplex. While full duplex is, of course, our roads here, that there is a left lane and right lane, and it can you can use the roads simultaneously. Okay, next is we have, must there exist a relationship, a parent or child between the communicating processes? Can the pipes be used over a network? So we have two types. We have ordinary pipes, cannot be accessed from outside the process that created it. Typically, a parent process creates a pipe and uses it to communicate with the child process that it created, while named pipes can be accessed without a parent-child relationship. So ordinary pipes, this is used by the parent and child process, while the named pipes can be accessed without a parent-child relationship. So for ordinary pipes allow communication in standard producer-consumer style. Producer writes to one end, the right end of the pipe, while the consumer reads from the other end, the read end of the pipe. Ordinary pipes are therefore unidirectional, so require parent-child relationship between communicating process. So that's why ordinary pipes are usually parent-child relationship. So for this illustration is we have, it illustrates the relationship of the file descriptor. So that's why we have the FD. Okay, then FD array to the parent and child process. As this illustrates, any writes by the parent to its right end of the pipe, the FD1, can be read by the child from its read end, the FD0. So this one. So for the FD1 of the parent, it will be read by the child for FD0. So of the pipe. So that is the illustration for the ordinary pipes. So these pipes for the parent and child, with the parent and child relationship, is called anonymous pipes. Okay, next is we have named pipes. So named pipes are more powerful than ordinary pipes. Communication is bidirectional. No parent-child relationship is necessary between the communicating processes. Several processes can use the named pipe for communication and provided on both Unix and Windows systems. So next is we have communications in client-server systems. So we have sockets and remote procedure calls, or the RPC. So first is we have sockets. So a socket is defined as an endpoint for communication, concatenation of IP address and port, a number included at the start of message packet to differentiate network services on a host. So the socket 161.25.19.8 colon 1625 refers to port 1625 and host 161.25.19.8. The socket is composed of an IP address and port. Then communication consists between a pair of sockets. All ports below 1024 are well known, used for standard services. Actually, I think you're going to study it in your networking subject. And then special IP addresses 127.0.0.1, or the loopback, to refer to system on which the process is running. Actually, this only pertaining to the machine itself. So actually 127.0.0.1, this can be used to test. For example, you have an HTML file and you want to know if it's really working. So the IP address that you're going to use is 127.0.0.1 to make sure that it is working for an HTML file, even if you don't have an internet connection. Okay, for we have socket communication. So this is the socket. It's a combination of IP address and a port for host X, and the web server also has its own IP address and port, which is port 80. Okay, next is we have sockets in Java. So three types of sockets. We have connection oriented, or the TCP, the transmission control protocol. This is the standard protocol used in the internet. And then we also have the connectionless, or the UDP, or the user datagram protocol. It is a communication protocol layered on IP that is connectionless. So that's why it doesn't have any connection. Low latency, so it is low. It is faster compared to TCP because it's low latency. But the only problem with connection with UDP is that it does not guarantee delivery. Okay. And then next is we have the multicast socket class. Data can be sent to multiple recipients. So consider this date server in Java. So this is an example of class date server and its code using with sockets, application for sockets in Java. Okay, this is the equivalent date client. And then okay, next is we have remote procedure calls. So remote procedure calls, or RPC, abstracts procedure calls between processes on network systems. So again, uses ports for service differentiation. So stubs, so RPC uses stubs, a client-side proxy for actual procedure on the server. The client-side stub locates the server and marshals the parameters, while the server-side stub receives this message, unpacks the marshaled parameters, and performs the procedure on the server. On Windows, stub code compiled from specification written in Microsoft Interface Definition Language, or MIDL. So data representation handled by external data representation or XDL format to account for different architectures. These architectures are big endian and little endian. So it's not, actually it has something to do Indian, but it just meaning big endian, meaning this machine, so big endian machines stores the most significant byte. So the most significant byte are on the left side. So what's the meaning of most significant? For example, we have, okay, for it's just an example. Of course, big endian machine stores the value in bytes. So I just want you to illustrate big endian and little endian. So example, we have value 9,000. Example. So if it is a big endian machine, so you're going to store the most significant bit or digit. So for this number 9,000, which of this is the most significant? Is it to the left or to the right? Actually, it is on the left. Most significant, of course. Why? Okay, so for example, this is 6. So why this is the most significant? Because it bears bigger value. The value from the left is bigger than the value relatively to the right. Example, is this 9 only? No, it's actually 9,000. While 6 here, it's only 6. So that's why the most significant digit is on the left. So big endian stores its value in bytes, the most significant bit, which is the left. While Lil endian, so that's why it's called Lil endian, it stores, these are the machines that stores the least significant bits or value first. So it stores first the 6 and then 009. So that is the Lil endian. For big endian, it will store 9006. Okay, then remote communication has more failure scenarios than local. Then messages can be delivered exactly once rather than at most once. So OS typically provides a rendezvous or a matchmaker service to connect client and server. So this is an example of an illustration of execution of RPC. So for the client, user calls kernel to send RPC message to procedure X. Then kernel sends message to matchmaker to find port number. And then this is the message from client to server, port matchmaker regarding the address for RPC X. And then the server will receive the message. Then the matchmaker receives the message, looks up the answer, and then the matchmaker replies to client with port P. So this is the message from server to client. Port is kernel regarding RPCX and then port is P. And then the client receives the message. Kernel places port P in user RPC message and then kernel sends RPC. Then the message from client to server, port P, and then the contents, and then the server will receive the message. Daemon listening to port P receives message, and daemon processes request and processes send output message from RPC, port P to client, port kernel, and then the output, and then it will be received by the kernel. So the kernel receives reply, passes it to the user. So again, this is an illustration of how a remote procedure call is used or executed. Okay, so this is the end of chapter 3. So I hope that you learned about the process, that the process is a program in execution. It has different process states and the different what is shared memory or message passing. So I hope that you've understand everything about the processes. So do you have any questions? If you do have any questions, feel free to comment below and please don't forget to subscribe to my YouTube channel. So thank you very much. Good day and stay safe.